The 1.3 notes focus on graphing in science. Why is this important and why are we reviewing it? Well, a graph is a visual representation of numerical data collected from an experiment. So every time you guys will conduct an experiment in this class, you will get data, and you're going to be expected to put that data into some form of a graph. This is an important step because it allows a large amount of data to be viewed and interpreted at once. And this helps scientists to more easily determine if data support a hypothesis. So when you guys make a graph in this class, you're going to be asked to interpret it and use it to tell us whether or not your hypothesis was supported or not. Well, what does a graph look like? Let's quickly review the different parts of a graph. We have two axes in this class, or in a scientific graph, excuse me. We have the vertical axis known as the y, and the horizontal axis known as the x. In science, this is significant because the different variables we have in our experiment go on a particular axis. For example, the independent variable goes on the x-axis. Okay, the independent variable is what is changed or manipulated in an experiment. On the y-axis, we put the dependent variable. This variable is what we use, this variable, excuse me, is what we measure in an experiment. So I'll show you some examples of that in a little bit. When we plot our data, it is plotted in this section of the graph. That all depends on the scale of the x and the y-axis, and that'll determine where the points go, or in some cases where the bars go, if we're doing a bar graph. Well, let's talk about that because there are different types of graphs. So the first type of graph we're going to look at is a line graph. A line graph uses points connected by lines to show how something changes in value. Let's look at an example. Let's say we're measuring how far something moves away from us over time. So in this particular case, our independent variable will be time because we want to see how far something moves away over time. So on the x or y-axis, we would put distance. And we might want to go ahead and make sure we label as well the increments of distance. For example, maybe it's meters that we're measuring. And on the y-axis, maybe we're measuring in seconds. What you would do is you would plot your points according to the values on the scale. And for a line graph, you would then connect those dots with a line. And that's what you would get. Okay, so that is what we call a line graph. Line graphs are typically the most common graphs that we'll do in a science class. But we have some other ones. For example, what we call a scatter plot. And we do a number of scatter plots in science as well. And this is what a scatter plot would look like. Let's say we wanted to find the ratio or see if there's any trend in height versus age, or how tall people are with their age. Well, what we're measuring in the population or in each individual is their height. And perhaps we do this in centimeters. And we would set our scale up to however many centimeters that we measure. And we want to see how that changes with age. So perhaps we're doing age in years. And then we would put ages down here. Well, for each individual, you would get a point. And you would plot that point. Every person would be different, and we'd see maybe some different trends there. So you might get in a scatter plot, get something like this. The important thing is in a scatter plot, we do not connect them with a line. So they're not connected with a line. We would just leave it just like this. This allows us to look at the overall trend. In this particular case, we can see that the data tend to be trending upward. Okay, this means that this is, we call this a proportional. Boy, that's not even spelled right. That's a proportional relationship. I'm not even going to try because my mind's not working right there. Try to spell that. If the data say we're going the other way, they were trending downward, that's what we call an inverse relationship. So we can see, take a look at that when we do scatter plots there. Okay, so that takes care of scatter plots. Let's take a look now at another type of graph known as a bar graph. Start out with our axes again. In a bar graph, we could be looking at a number of different things. Perhaps we want to look at let's say we're going to do a histogram of the age of fish that we catch. So here we would put the age in years of the fish, and then here we would put the number of fish caught. You would go ahead and plot your data then as bars. Some people call these columns. In a typical graph like this, if you're looking at the age structure of fish caught, or even regular or other animals being caught, you would get something like this. You'd have a trend downward, okay, and that would be what we call an inverse relationship. We catch fewer fish that are older, and that's typical in any fish population that we would be looking at. So that's an example of a bar graph. And then the last type of graph we're going to talk about is a pie chart. And this is a circular chart that's divided into sectors, just like a pizza. And hopefully you've seen one of these before. The thing about this is that there's no axes. It's just a circle. And we can use this typically in biology. We can do biodiversity data like this, showing the proportion of different species in a particular population. So for example, maybe in a given habitat, maybe we have an awful lot of insects. And you can write the percentage. Maybe this is 40% insects. Then we have maybe a bunch of birds, mammals, etc. And again, this is just an example. This isn't real data, but just to show you how a pie chart works. So we'll make pie charts when we are doing biodiversity studies later on in the class. But those are the different types of graphs. I just wanted to show you how they work.